Good afternoon, everyone. Welcome to the TSGC Design Challenge. My name is Tim Urban. I'm the director of the Texas Space Grant Consortium. With me online are Talia Jurgens and Angelica Cruzinga to support the showcase today. We have 17 teams this semester. 9 of them are presenting this afternoon. And they are going to be in 3 sessions, 3 teams each. They're going to have 10 minutes to present, and then a 5-minute question and answer session. All of our question and answer sessions are going to be hosted through the slido.com app. So go to slido.com and use code TSGC 2021. Once you do that, you'll enter our Q&A session, as well as be eligible to vote in polls. After each team presents, you'll be able to rate them with 1 to 5 stars. If you have any questions about Design Challenge, our email address is there on the bottom left. And you can check out our website, tsgc.utexas.edu/challenge, and find more information about the challenge, as well as the teams. We have our schedule listed there, background on each team, and our feedback forms for the teams. If you'd like to be a judge and look at their virtual videos, virtual posters, or these presentations themselves will be archived there. Please do so. The feedback forms will be open until Sunday. This is a list of the 9 teams we have this afternoon. In session 1, we're going to play all of their 1 to 1.5 minute elevator pitch videos. Then we have Texas A&M, UH Clear Lake, and Lamar University, followed by session 2 and session 3. All right, and
future Artemis astronauts are going to require a safer and more effective way to complete tasks on the moon. To address this, NASA issued the NASA Suits Challenge, encouraging students to improve astronaut extravehicular communication with augmented reality.
The 12 Astronaut Lab aims to develop and optimize a user interface that can be integrated into the extravehicular mobility unit of astronauts.
Working with Microsoft HoloLens and Unity Game Engine, our team aims to bridge VR and AR technology in order to establish an alternative means of communication between intravehicular and extravehicular astronauts.
Our solution to the NASA Suits Challenge is Scout, an augmented reality assistant with an elegant user interface, navigation capabilities, a science sampling system, and the Telepresence Whiteboard.
Scout consists of floating hologram panels that display key vitals, task checklists, and settings to change font size, color, transparency, and feel of the system, which are all easily accessible via our main menu.
Scout provides an augmented reality compass and virtual markers to safely guide the extravehicular astronaut to points of interest.
Lunarpedia serves as a virtual science sampling logbook, which the astronaut can use to save pictures and notes about anything that they find while in the field.
The Telepresence Whiteboard allows mission control and intravehicular astronauts to spawn holograms and drawings directly in the extravehicular astronaut's field of view, allowing for more interactive communications.
Lastly, our team is developing a robotic assistant to aid the extravehicular astronaut in reconnaissance by mapping out the upcoming terrain and sensing major obstacles or hazards.
We are NASA Space Grant!
Hello everyone, we are Team Ad Spatium from the University of Houston Clear Lake. My name is Hudson Hill, and I'm the team leader and a senior mechanical engineering student.
My name is John Crocker. I'm the deputy team leader, and I'm also a senior mechanical engineering student.
My name is Mustafa Haider, and I'm a senior mechanical engineering student.
My name is Ji King Bun, and I'm a senior mechanical engineering student.
And we are pursuing the Micro-G Next Lunar Reusable Anchoring Device Design Challenge that we have titled the Lunar Locker.
In the upcoming Artemis mission, NASA is sending the first woman and first person of color to the moon. The astronauts will need the ability to anchor themselves and equipment to the lunar surfaces while conducting EVA experiments.
The anchoring device has to comply with multiple criteria and constraints to qualify for the challenge. The most crucial of them being completely mechanically powered and the ability to produce 10 pounds of holding strength.
In order to properly aid in EVA operations, the device itself must be lightweight and small enough to fit inside a cylindrical transportation device. Once the lunar locker is removed from the container, the user can simply rotate the shaft handle counterclockwise to deploy the claw mechanism. And once a suitable location on a rock surface is found, rotating the shafts clockwise will close the claws to grip onto the rock surface. Thank you for watching our video.
We are NASA Space Grant.
This is Team Atlas from Lamar University, consisting of myself, Jorge Magaña.
Me, Adrian Galvan.
Me, Adrian Espinoza.
Me, Alexandra Villanueva.
Me, Lisette Aguilar.
And me, Mason Munoz.
So our project is to design an antenna mounting structure for the Nova C lander set to land on the moon in early 2022. We were given a mission by our mentor, Chatwin Lansdowne, to discover the feasibility of transforming the lander into a cell tower capable of achieving a coverage radius of approximately 10 kilometers.
We were able to devise a deployable design capable of surviving extreme lunar temperatures and conditions while maintaining a lightweight and compact design.
The team ended up choosing a telescoping mast mechanism that extends the structure using pulleys and a motor. This design should withstand vibration, buckling, and thermal simulations. Among several other design candidates, we chose this one because of its reliability and stability.
We determined that aluminum 6061 was the best candidate due to its thermal resistance and structural stability.
The team was able to keep the package just over 6 kilograms, even with an extreme safety factor, which meets our customer requirements.
Thank you for watching our video.
We are NASA Space Grant.
Hello, we are Team HDS, and we will be doing the Machine Learning Human-Computer Interface System project for NASA.
Missions in space can both be long and stressful, and as a result can take a toll on astronauts. Therefore, it is necessary to monitor their physical and mental health to ensure the well-being and success of the mission. If an astronaut's performance begins to degrade due to stress or injury, there must be a system in place to ensure successful completion of tasks, even if the astronaut is rendered incapable. The greater the distance from Earth, the longer it takes for communications to take place between Earth and Space Shuttle. This system should help provide astronauts with immediate responses in the absence of human assistance back on Earth.
We will be developing an application with the purpose of simulating possible emergency events that could occur during manned space flights. Machine learning will be used to assist the users in the operation of the systems module and to identify any degradation in the user's performance baseline. In the event that a user is unable to properly operate a module, the machine learning aspect will be able to autonomously interact with the module without the need of the human operator.
Our project will consist of 2 modules to simulate possible emergencies that could occur in space and will be connected through a central controller which is interfaced via a touchscreen graphical user interface. One module will be for detecting and avoiding potentially hazardous objects by using multiple ultrasonic sensors in a live camera feed. The second module will be used to detect the outbreak of a fire using thermal, temperature, and humidity sensors. The system will then direct the user to the fire's location and assist the user in following the proper procedure for fire suppression and damage control.
We are NASA Space Grant.
Hello, I'm Jonathan Johnston, team lead of Team Solis. We are NASA Space Grant.
Hi, I'm Mohammed Wahid, Secretary of Team Solis, and we are NASA Space Grant.
Hi, my name is Victor Ortiz. I'm the Vice Officer for Team Solis, and we are NASA Space Grant.
Hi, my name is Deval Patel. I'm the Treasurer for Team Solis, and we are NASA Space Grant.
Hi, my name is Christopher Contreras, and I'm the Communication Officer for Team Solis, and we are NASA Space Grant.
The team's objective was to design a reusable lunar anchoring device for astronauts in the Artemis mission.
This current prototype meets the requirement with its ability to anchor to at least a 12-inch diameter rock face while bearing angles to 90 degrees and maintaining a closing force of 10 pounds. In addition, it weighs 3.7 pounds, is compatible with EVA gloves, and can be manually operated with 1 or 2 hands.
Argo, named for apparatus for rock gripping operations, is 17 inches tall and 5 inches in diameter. There are 5 segmented limbs with angled spines for maximum grip and hold. Ice was a consideration in the model due to the ice exposure that would take place in the Artemis mission. The spines hook into the ice without penetrating the rock surface.
In addition, the device will utilize a cable connected to the outermost end of the limbs and exert a contracting force which will curl the limbs inwards, much like the end of a finger, to anchor them to the rock.
I am Team Silas.
I am Team Silas.
I am Team Silas.
I am Team Silas.
We are Team Silas from Lone Star College Side Fair. And we are NASA Space Grant.
Welcome to the West Houston Institute, located at the Houston Community College Center of Engineering, northwest of Houston. Behind us is where all the magic happened. Follow me as I take you on a tour showcasing the results Team Eagle has produced for the TSGC NASA Design Challenge.
Since the dawn of space age, mass and volume has always been an obstacle to overcome in space exploration. As a team, we made our primary objective to optimize our design with mass and volume in mind to reduce mission costs. We did this with the art of origami, an ancient art that in recent years has been utilized as a vital tool in engineering and design. With origami, we designed a bed frame that is not only lightweight, but is incredibly strong, easily assembled, and mass producible.
Starting with the first iteration of our design, we implemented the Miori folding pattern into a small sheet of paper, and the structure could actually, surprisingly, hold a tremendous amount of weight compared to its own. We moved up to a scaled-up model version of the same pattern on the same material paper to understand all the complexity of this folding pattern, which then we implemented our learnings into our first prototype that was built with the desired materials.
Based on our prototype, we made several iterations for our testing phase. The calculated threshold was 40 kilograms or 400 newtons. We are NASA Space Grant.
Hello everyone, my name is Juan Pablo and we are Houston Engineering Center Group 5. I'm going to present Vehicle Interchangeable Electronic Network System.
Our design uses Arduino for all controllers. Why we use Arduino? Because it's easy to use, accessible, and affordable.
The project simulates 4 vehicle application: light, temperature, air pressure, 3-axis acceleration. Each application has a LED to display the status. We use the dip switch to request the suitable behavior from network server as a potential identification.
For our sensor, we use I2C that stands for Inter-Integrated Circuits for data communications from the application, agent, and main controllers. For our network system, we use Ethernet network communication to communicate between the controllers.
For our design, we use a common connection for all unit and receiving power. A common 9-volt battery can power the controller.
We make a backup for network system. If one of the controller is going to fail,
any other controllers can replace it, then behave according to the position.
This is our design proof of concept. Our future plan is to make it fully functional and efficient. We believe this will be the best fit for the challenge.
We are NASA Space Grant.
Good morning, Team Red. Welcome to the University of Houston. NASA will be returning to the moon through the Artemis program. As part of the program, astronauts will be tasked with collecting and documenting lunar samples as part of the extravehicular activity. As a result, Team Red came up with an innovative solution to document the sample information and location. Our design called GEO is a lightweight, safe, easy-to-use device, and it can be deployed and retrieved without the user kneeling all the way down. The device is compact when stowed away, locking itself into a triangular prison, easy for storage. Also, Geo can be easily deployed only using manual power. Displaying its color preference is still visible from all angles. For all these reasons, Geo will become a valuable tool to study the lunar surface.
My name is Humberto, and we're NASA Space Grant.
Hello, my name is Rogelio.
Hello, my name is Celine Cherrier, and we are NASA Space Grant.
I am Selene Mystery, and we are NASA Space Grant.
Hi, I'm Harry Goldberg, and we are NASA Space Grant.
Okay, great introduction teams. So that was a brief summary of the 9 teams we're going to have presenting today. Every team will be promoted from an attendee to a panelist. And then when it's your turn, you can turn on your video and audio. Our first team is going to be 12th Astronaut Lab. Audience, if you could visit slido.com, you can begin to put in your questions for the question and answer session, as well as vote in the poll that will open when they're done presenting. So 12th Astronaut, are you ready? Give me a thumbs up if you're ready. You are ready. All right. You should be able to share. Take it away.
Apologies real quick. It looks like it's still sharing. There we are. Okay. There we are. So howdy. Thank you, Mr. Urban. So we are the Texas A&M 12th Astronaut Lab. Let's see. Here we are. Here are our TSGC team leads. And here are advisors, Dr. Anna Diaz and Dr. Gregory Chamadoff. So what is NASA Suits? NASA Suits is a software challenge that serves as a stepping stone for alternative methods of communication in space using augmented reality. This challenge will lead towards AR implementation on the new EMU spacesuit during the Artemis campaign. So our solution to the NASA Suits challenge is Scout. And looking at this design overview, you can see that Scout is designed into 2 main parts, our AR assistant and our robotic assistant. Scout's AR assistant informatics will display science instructions, vitals, terrain, and navigation instructions, which can all be manipulated in real time. Scout's robotic assistant serves as a reconnaissance robot that creates a mesh of an upcoming terrain via a LiDAR sensor in order to identify hazards and obstacles and route the best way to certain objectives. All of this is displayed and communicated via Microsoft HoloLens 2.
Hey everyone. The mobile robot assistant is a telerobot that will aid the EVA crew member in navigation, reconnaissance, and sign sampling. Our robot base is built off of a Yaboom G1 AI Vision Smart Tank robot, which features continuous tracks, Raspberry Pi, and real-time video transmission. The robot can explore dangerous areas and assist in search and rescue. Video feed can be supplied to mission control for better personnel support.
To further assist with navigation, we've created an adaptive navigation system, which involves the use of machine learning through Unity's ML agents. First, the surface normals are identified from the camera, and the crater boundaries are retrieved from a database, which are both input into the neural network for the agents to use. Then the agents utilize this data to create a suitable path to the current objective. As seen in the video, the agents, which are marked in blue, are exploring the virtual lunar landscape and are gathering data in order to provide a database for avoiding hazards, which are marked in red. Once the agents are sufficiently trained, they can be deployed to help assist in avoiding hazards and create a more efficient and safe path.
Another component implemented is our UI compass, and it interacts with its pointer to display the location of interest, such as a rover or lander, in relation to the EV crew member. The name and distance of the object is displayed overhead. The points rotate to indicate the appropriate direction of the waypoints. As seen in the video, the user is selecting waypoints from the navigation menu to display on the compass. These markers can be set by the EVA or IVA crew members before and during the spacewalk. This compass serves to provide a sense of spatial awareness in bare environments such as the lunar landscape.
A feature we have for field note-taking is the Lunarpedia. And the Lunarpedia note-taking system is used to create, store, and recall entry logs. The user can create an entry, add a picture and description using the voice logs, and store its location as a spatial anchor as shown in the top photo. The Scout Assistant takes care of real-time voice transcription using the Azure Cognitive Services framework. Once the user saves the log, it is saved as an object in the Azure Blob Storage resource. The user can also display and edit any previously created log and location, and the photo and description will be updated in the cloud storage, shown in the bottom photo.
Scout's AR Assistant also has integrated Azure Custom Vision machine learning for object detection of various items, including extracurricular activities, and can be used for tools such as science sampling and rock sample.
Our user interface design features circular consumable level indicators that are updated in real time based on the telemetry provided by the spacesuit. It also has a Lunarpedia, which again can be used to record voice logs and catalog pictures of science samples and points of interest found in the field. Our radial menu makes it easy to access any UI elements quickly through eye tracking and hand gestures. And lastly, the 3D Terrain Minimap provides a visual of nearby waypoints, crew members, locations, and hazards. The 3D Minimap uses a combination of data from the Lunar Reconnaissance Orbiter and real-time scans to generate a miniature representation of the environment. The more saturated a color is on the map, the more hazardous that region is for the astronaut. It also serves to display route options determined by Scout's reinforcement learning-based adaptive navigation system. The map will display the most ideal path of travel towards a specific destination based on current consumable levels, lighting conditions, and proximity to nearby points of interest.
Here is the Telepresence Whiteboard. The video on the left shows the view from the remote user or mission control. The video on the right is the view from the HoloLens 2 user or the astronaut. The remote user can see the scene that the astronaut is in using the LiDAR scan data. The position of the astronaut is indicated by the VR headset. The position of the remote user is indicated by the Scout AR Assistant icon, which looks like a Shiba Inu. Using the Photon server library for networking, the remote user can then guide the EV crew member using the spline pen to draw on the EV crew member's field of view, as you can see with the blue drawings in the video. The remote user can also speak to the EV crew member. Scout AR Assistant can suggest in real time to the astronaut crew member different recommendations of where to go and what to look at. Scout can also listen to and interpret voice commands from the crew member to change the UI display.
And thank you for attending our presentation. We are NASA Space Grant. So if you have any questions, here's a convenient QR link for Slido. And please feel free to visit us at 12astronautlab.com. So I think we're good for questions, Mr. Urban.
Absolutely. Thank you very much. Let me share my screen again. Okay, there's 12th astronaut. Again, audience, go ahead and use Slido. I will open up the poll. Go ahead and vote for the team and ask your questions. So let me ask one while people are typing. Was the robot part of the challenge this time or just something you added?
The robot was part of the challenge this year for returning teams. So teams such as myself, I believe last semester, the University of Houston Bavitsma team, all eligible to create robotic assistants this semester, this challenge.
Okay, and then is the robot for on the base, or is it supposed to operate on the surface of the moon?
It's supposed to operate on the surface of the moon. So in our case, our robot serves as a reconnaissance robot, creates a mesh of all the surrounding terrain. and just sent it back to both EVA and IVA astronaut along with mission control. So, but regarding that was our idea. I believe every team would have their own individual and unique idea for the robot.
Okay, and did you consider dust on the lunar surface with your robot?
We did. It's something. So usually, as I'm sure you're aware, we're usually a software team. So this is our first year doing something hardware related. We have considered that, but so far the only what's the word I'm looking for? The only consideration we had for that was just to do our best to copy and paste what NASA already has for robots, both on Mars and I believe they have 1 or 2 on the lunar surface.
And I'd like to add on to that. We did a review of literature and we found some papers on electrostatic dust mitigation, where you can use an electrostatic field to kind of collect the dust in one area and get it away from some of the joints of the robot. So that's one thing we did look into.
All right, great. All right, another question then. You mentioned the compass. Is there enough magnetic field on the room or on the moon to use a compass like it would on Earth, or how is it referenced?
I can answer that.
Okay.
So the way the compass works is it's not necessarily using the magnetic poles, but it's using the location of the EVA person and the astronaut as a way to like triangulate and map out, I guess, in a way. It doesn't serve as a way to give them a like north and south, but rather a general direction so that they know like a general area. So it's more of a 180-degree type of arrow that tells them, hey, if the mission control wants you to pick up a rock that's behind you, you know, you can drop a waypoint and the compass would just give you a general direction of if it's like 20 degrees to your left or 20 degrees to your right. And the way it does it is when the HoloLens scans a room, it's able to, with the 3D mesh, you're able to see exactly what they're seeing. And so it makes like another virtual world for the IVA crew member or the person using the Scout assistant. And they're able to actually like drop the points where they want them to go. And the code would just simply, I guess, in a simplified way, just rotate on that horizontal compass where he has to go.
Okay, so it's a relative direction based on where you're at. I understand. Mm-hmm. So what were your biggest challenges this semester as a team? You are a returning team to the Suits Challenge as well as Design Challenge. So what were your new challenges this semester?
Our biggest one was definitely the robot. Also, we are still researching and looking to adding peripheral devices such as a flashlight and such as a flashlight on the HoloLens. So I believe our biggest challenge are more mechanically oriented this semester. But other than that, our software team has been the exact same, and we're not the exact same, but we're expanding on ideas we've had in previous semesters and previous challenges.
And I can add on to the robot challenge. On the robot to make a scan of the terrain, we had to figure out how to get a low-cost LiDAR sensor on there. But there's a lot of data in that, and we're using some machine learning algorithms to identify hazards and trying to figure out how to get a whole computer that could fit on the robot miniaturized was really tough. But we decided to use a small board by NVIDIA to work with that.
All right, excellent. Thank you very much, 12th astronaut. All right, we are going to go to our next team, University of Houston Clear Lake, Team Ad Spatium. And let's check to see if they've all been promoted to panelist. 1, 2, 3, 4. All right. Team, are you ready?
Yes. Can I take over the screen sharing?
Absolutely. Go ahead.
Thank you. All right. So we are Team Ad Spatium from the University of Houston Clear Lake. My name is Hudson Hill, and I'm the team leader for our design group.
My name is John Crocker. I'm the deputy team leader.
My name is Ji Kim Bun. I'm a team member.
My name is Mustafa Haider. I'm a team member.
And this year, we've decided to pursue the MicroG Next Lunar Reusable Anchoring Device Design Challenge. I'm now going to pass it on to Mustafa to discuss the project background.
Thank you, Hudson. So for the project background, in 2024, NASA plans on returning to the moon with the Artemis program. And this is the first of its kind since Apollo 17, which took place in 1972. As part of MicroG Next Design Challenge, they've requested the creation of a lunar reusable anchoring device, which will help them in EVA mission operations. There were several criteria and constraints that had to be followed in order for a feasible design to be implemented and to be used on the lunar surface, specifically the south pole of the moon. For project goals and summary, we have to maintain good standing with TSGC and MicroG Next. They had several due dates and deliverables that were scattered throughout the semester. And with submission of each deliverable, we got closer and closer to our final goal, of course, which was to design and develop a lunar anchoring device with full mechanical functionality. And the design, it can't just look good on paper, it also has to be practical in a real life application. And that includes, of course, the assembly of the design itself. I'm going to pass it on to Bun to talk about the criteria and constraints.
Thank you, Mustafa. Listed here are the criteria and constraints given by MicroG Next for the design challenge. It is essential that we meet each requirement, but there are some requirements that are more important to the development of the design concept. The first constraint is that the device must be mechanically powered, meaning there can't be any use of pneumatics or electrical equipment to power the device, and it should only be operated with gloved hands. The device also needs to be less than 5 pounds and be able to fit into an 18-inch long cylinder container with a 6-inch inner diameter, which greatly affects the overall constraint of the device. Also, it must provide 10 pounds of holding strength without penetrating the lunar rock surface. Now I'm going to pass it on to John for the first conceptual design.
Thanks, Bun. The first conceptual design is shown in Figure 1. This design utilized a pulley system to apply tension to cables to pull spring-loaded legs inward to grasp the surface of the lunar rocks. The main mechanism was a shaft with an attached handle. The handle is where the astronauts would apply torque to drive the externally threaded shaft through the internally threaded body. As the shaft moves through the internal threaded body, the movable bottom plate moves downwards, pulling the cables into tension. The pulleys shown guide the cables linearly through the stationary top plate. This design ultimately created additional barriers in the design process, as the design would exceed the allowable 5-pound limit. This conceptual design would also be difficult to manufacture, as the components needed would be too difficult to assemble for a small device. I'm going to pass it on to Hudson for the second conceptual design.
Thank you, John. For our second design concept, we actually had the opportunity to attend a MicroG information session. And during that session, it was described that the device itself could be used to grab onto the rock as if to lift it, instead of trying to utilize the face of the rock surface as seen from our first conceptual design. In the second conceptual design, it is still powered by torquing a threaded shaft component, and it allows a lead screw to be able to traverse the shaft. The idea for this concept is that the threads are self-locking, or potentially adding an additional locking mechanism so there's no back driving of the threads when it is locked onto the rock surface we're trying to attach to. I'm now going to pass it on to Bun to discuss our decision matrix.
Thank you, Hudson. In order to select the best conceptual design, a decision matrix was utilized in order to highlight the strengths of a specific concept design. NASA's InSight Mars lander space claw was used as a datum to compare with the given design concepts. Going through the matrix, it is shown that the second conceptual design was rated higher than the first conceptual design with the given criteria. With this breakdown, it was estimated that the second concept would be the better design moving forward. Now I'm going to pass it to Hudson for the final design concept.
Thank you, Bun. So our final design concept, it still utilizes the lead screw to generate linear motion as was previously shown in our second design concept. The lead screw is flanged to a bottom plate that will allow the legs of the claw device to open and close based on the linear motion of that lead screw. The bottom of the claws have a rubber footing that will ensure that there's no penetration and a strong grip could be achieved on the rock surface. The design in the figure shown is mostly based on the Micro-G Next design challenge and that it will be potentially tested in the neutral buoyancy lab, but there have been some considerations for use on the lunar surface, such as a rubber seal to protect the thread interface surface from any lunar dust. I will now pass it on to John to discuss the material selection for our design.
Material selection for our final conceptual design consists of 4 main materials: 6061 T6 aluminum, 304 stainless steel, 316 stainless steel, and nitrile rubber. The aluminum was chosen for the main components listed in Table 3, such as the strut, leg components, and bottom plate, and stability handle. The 304 stainless steel we chose for the lead screw and threaded shaft, along with 316 stainless steel for the fasteners and strut hinge. And finally, nitrile rubber was chosen for the claw foot. Nitrile rubber was chosen for the claw foot mostly because it has excellent abrasion resistance. Since lunar rocks are very porous, we didn't want our bottom material to break off, or we needed really good tearing resistance as well. We chose a 6061 T6 aluminum for its strength to weight ratio, its corrosive resistance, and its rigidity for our design. We chose 304 stainless steel for our lead screw and threaded shaft because of its corrosive resistance and good rigidity and weldability. Also, 316 stainless steel for fasteners and strut hinges. We mostly chose those because of a corrosive resistance, and 316 stainless steel is mostly used for fastener applications, stuff like that. For the material weight, the total weight for all components is listed in Table 4. Each component and its quantity and its corresponding total weight can be seen. The total weight for all of the components needed for our design was around 4.924 pounds. The total weight was evaluated using SolidWorks mass properties for each material and its corresponding component. The total weight for all the components is cutting it close to the 5-pound constraint. So further building and prototyping will be necessary to ensure the device is within the constraints for Micro-G Next. I'm going to pass it to Hudson Hill for the clamp and thread analysis.
So the first bit of analysis that was performed was to see how much force was required to generate the 10 pounds of holding strength needed for the claw device. This was done with the use of MathCAD, and the calculations show that each leg is subjected to around 11 pounds of force. This value can then be used in finite element analysis to ensure the structure of the device can be strong enough to withstand the desired holding strength, and this analysis will be performed at a later date for the structures. The last bit of analysis was for the threads in the design. As previously stated, one of the goals is for the threads to be self-locking so that we don't have to have the use of an external braking system to hold the threads in place. The thread we chose is a 1 1/4 inch thread diameter with 4 threads per inch and 2 thread starts. A minimum friction coefficient of 0.15 for steel-on-steel thread interface was used in the analysis and shows that the threads, in fact, should be self-locking. Further testing will still be done in prototyping to ensure that these threads are self-locking will be safe for the design that we've chosen. I'm now going to pass on to Mustafa to discuss the project plan.
So what's been done so far, as you were previously shown, the conceptual model has been designed and the parameters have been evaluated, such as the weight and the material selection. Going forward, we will await Micro-G's final decision on the design selection. And should Micro-G choose to select our design, they will appoint us a mentor, which will help us immensely, of course. And we have to perform finite element analysis on the structural components. And we have to create our design prototype and evaluate its effectiveness. If there's any errors or issues that we encounter with the prototype, or if it's not up to standard with the criteria and constraints, then we will make adjustments as necessary to produce our final working product. Thank you for watching. Are there any questions?
All right, thank you very much, Clear Lake. Okay, everyone can see the screen again with the code TSGC 2021. Go to slido.com. You can ask questions, upvote questions, and take our poll. For the audience, go ahead and ask questions while we're waiting for them to type. Let me ask about dust. So dust is a big consideration on the moon. What have you done to mitigate the dust?
So as mentioned in the slide, we thought about it somewhat in terms of protecting the thread surface, because if any dust were getting there could gall up and damage the thread surface. The main concept that we've come up so far, it was mostly for micro G in terms of testing in the neutral buoyancy lab, but we've considered adding some sort of like a rubber surface to protect and keep threads out of that thread interface section of our design concept.
And were you given any parameters for how long it would be used, either number of excursions per day or even a lifetime?
Yeah, there's no specific lifetime given from what I remember and know from the given constraints and the info sessions from Micro G. The constraints and requirements were pretty broad, even when they're describing in their info sessions, and it made it seem, or they spoke about how they want to kind of keep the concept and the challenge as open as possible so they can grab different ideas from multiple teams rather than sticking to like a super specific design concept.
Okay, we've got a question here. Let me read that. Have you considered providing a motor drive? Seems like this would take a lot of time to grasp a rock.
So with the constraints and requirements from Micro G, there is no additional or outside use of any electrical equipment or pneumatic equipment. It has to be powered by the astronauts themselves. The lead screw that we've chosen in the thread design allows for a 1/2-inch lead, and there's only about 3 inches of thread interface to fully open and close the device. So it would take about 6 full rotations of the threaded shaft in order to go from a closed state to completely open for the 12-inch diameter surface it's trying to capture.
Okay, very good. The feet you said were made out of rubber. What's the lifetime of that on the moon? Do you have any idea?
Do you have any input, John, on that?
No, not specifically. However, there's a lot of rubbers we could have chose. But we have really no data about the rubber life on the moon specifically now.
Be something to look into for sure.
Yeah, definitely.
But then again, we were also not given specific expected lifetime from the design challenge of Micro G.
Right, as you said, yeah, they kept it pretty open. So what's been your biggest challenge so far this semester?
I think the fact, especially from the beginning with the design concepts, of kind of narrowing down of how we want to approach the design, because it is kind of open. And when we would ask questions during the info sessions of Micro G, they still answered in a very open manner. So we had to have a lot of decision making in terms of like what type of design we want to narrow in on and what would be more feasible and easier to use while in a Micro G or microgravity setting.
All right, very good. Well, thank you very much, team, and good luck.
Thank you.
Thank you.
Okay, our next team is going to be from Lamar University, Team Atlas. And they're going back to the moon with an antenna mounting structure. Is everybody online? Okay, when you're ready, go ahead and share the screen and you may begin.
All right. Hey everyone, we're Team Atlas from Lamar, and we've been working on an antenna mounting structure for a lunar lander. Our faculty advisor is Jenny Zhao, and our NASA mentor is Chetwin Lansdowne. So here's the outline of our presentation today. We will be starting with a brief introduction of the team and the problem definition. We will be covering our engineering specs, conceptual designs, concept evaluations, materials, analysis, CAD models, simulations, some problems, and our future work. Here you can see a group photo for a team. Starting from the left, we have Jorge Magaña, Adrián Galván, Alexandra Villanueva, Adriana Espinosa, Lisette Aguilar, and Mason Muñoz. So antenna installation heavily depends on the antenna mounting structure, as it often determines the size, weight, cost, and schedule. Our team is specifically assigned with designing an antenna mounting structure that will attach to the lunar lander Nova-C, and that will be significantly long in order to maximize antenna coverage. This structure also needs to be deployable on the moon, and because our structure needs to be very long, it needs to be compressible to reduce space during transportation from Earth to the moon. Once it's there, it needs to be deployed. The objective of this project is ultimately to propose and explore novel concepts for an antenna mounting structure free of specific mission imperatives, and the project will produce several options and then prototype and test at least one of them.
Here are engineering specifications. It has some of the most important requirements we need to consider, such as weight, height, temperature, vibrations, and dust. Going into more detail, it is expensive to send structures into space. It costs up to $1 million per kilogram to send something into space, according to our mentor. For this reason, we want to keep our weight to a minimum. Our team aims to keep the total weight under 10 kilograms. Another thing to consider is the extreme temperatures on the moon poles. The temperatures there range from negative 280 degrees to positive 260 degrees Fahrenheit. So we need to pick a material that could withstand these temperatures. In addition to extreme temperatures, we must consider significant vibrations that could affect the structure during launch and landing of the lunar lander. Therefore, our design needs to have the structural integrity to withstand these vibrations. How we would attach the antenna bracket to the Nova-C was also considered. The Nova-C has a solar panel structure on top, so we determined that we would need to attach our structure on the side panels. Following the antenna placement, there's also 2 antenna possibilities to choose from. The team can choose between long-range or lightweight antennas. Since there needs to be space within the structure to allow for cables, the structure needs to be designed in a way that the mechanism will not be affected by any dust found in the moon. Moreover, the landing site will be in a raised lip of a crater, not affected by, And there's a possibility that the lander lands in a 10-degree incline, so a mechanism is needed to adjust the antenna if the lander does not land straight. Finally, we will need to be able to accommodate for a 20-year lifespan and endure 2-week cold soaks.
So for our conceptual designs, we came up with 3 deployable variations: a telescoping boom, a composite boom, and a triangular truss. The telescoping boom is composed of multiple hollow tube sections that are initially stowed and deployed one at a time. And this is done by an electric motor that sets a system of pulleys in motion. This concept provides great structural integrity. Then there's the deployable composite boom that is very much like a measuring tape and is made out of composite materials. The boom contains strips that are either glued or welded together and shaped in the form of a cylinder. The motor and boom are housed in the same space that then leads to a tubular opening from which the boom deploys. Lastly, we have the deployable triangular truss, which consists of metallic wires that uncoil from the base of the structure by a motor and a turntable. This design offers a compact storage volume that occupies less than 50% of the total deployed length. Since it's foldable, the joints have multiple degrees of freedom, while the truss structure offers structural support.
All right, so after we did further research on the 3 concept designs for deployable structures, we were actually able to evaluate the 3 designs against each other based on the criteria listed in the matrix chart. We provided specific ratings on each deployable structure, and after adding up all the scores, we were able to choose the telescoping mast as our main concept. Since the telescoping mast was chosen as our main concept design, we then focused on the material selection for the mast. So we went ahead and created a material decision matrix where we evaluated aluminum 6061, 2024, and 5052 We chose to evaluate these materials based on the criteria listed that we believe were extremely important, and I'll talk more in depth on the materials in a bit. But after adding up all the scores for each material, we were able to select aluminum 6061 as a material that we'll use in our telescoping mask design. As mentioned, I did want to go a little in depth in why we specifically chose to evaluate aluminum alloys. We decided to study this material since it has a long and successful history in aerospace, where it has the ability to withstand vacuum and extreme conditions. Since there are several groups based on material characteristics, we decided to narrow it down to 3 aluminums, and we use this chart on the right to help us score these materials on the decision matrix, where, as mentioned previously, chose aluminum 6061 as our material for this design.
So we began design for the mast by using a preliminary model based on Euler's column buckling theory to guess the thickness of the mast. This model was performed using different heights, and we found that 6 feet was determined to be the most achievable in our time span. This would put the tower at about 14 feet, including the lander height, and the figure on the right is colored by critical loading in pounds. So our load lies well within the bottom left region, and we knew using a thinner mast was achievable. These are the formulas and conditions used in the Euler's column theory graph. The pulley system is how the mast is going to get to its deployed position. We studied countless other deployable masts of all types and came up with this simple lightweight option that gets the mast to its desired height. A force analysis yielded a torque value of 0.48 Newton meters for our motor, and the Nippon Pulse stepper motor met our criteria. A preliminary radio link design was performed with the help of our mentor to determine a rough estimate of the required antenna EIRP for varying tower heights. While our antennas were roughly picked out for us, this model may be useful in the future to determine other alternatives. Mr. Lansdowne also helped us pick out a suitable cable by comparing their masses and insertion losses. From his research, the UFJ 205A and UFJ 185A were both good candidates to use. The cable selection is important in our project in determining the maximum range of antenna, as well as a more accurate load for the buckling simulation, as we'll see in the future.
So here are some of our CAD models. These are specifically of the mast. You can see both the stowed and deployed configuration of these. And while stowed, the mast will only be 27 inches, which is 2.25 feet. And when deployed, the mast will reach a height of 6 feet. And here you can see our motor and spool. The motor will drive the rope that will power the mast through a simple pulley system. And there will be a housing that will sit on top of that to serve as a stable transition between the motor and mast. And then here is our final configuration. The weight of the assembly was 13.5 pounds. We include an enclosure around the mast and motor assembly to connect it to the lander's panel, and also to protect the structure's mechanisms from lunar dust upon landing. As of now, the top is open, but the team plans on having an automated lid that will open upon safely landing. And the housing of the motor can be seen in both of these views. In order to make the structure, in order to make sure the structure would be able to withstand the top load, we conducted a buckling simulation using gravity and an estimated weight of the antenna and an auto-adjusting mechanism that we're planning on also doing as the loads. The following results were obtained, and since the load factor is considerably larger than 1, the mast will not buckle.
Some potential obstacles that may be faced when landing may include an uneven landing and the abrasive lunar dust. Fortunately, the Nova C lander has an approximate 10-degree tilt recovery, but in order to maximize the antenna range and efficiency, we plan on adding a gimbal at the top of the antenna mast for stabilization. Furthermore, in order for the deployable structure to be free of lunar dust, we have added a casing around the mast, and we will design a lid on the top. In the foreseeable future, we plan to prepare our CAD models for manufacturing, then building and testing our prototypes. And our prototypes will be made of the selected material aluminum 6061, and we will perform vibration tests. Finally, we will design and program both the gimbal and lid to deploy once landed. And the team would like to give a quick shout out to TSGC, Tim Urban, Chatwin Lansdowne, our project mentor, Jenny Zhao, our faculty advisor, for helping us along the way. And here are some of our references. And does anybody have any questions?
Okay, thank you very much, team. Audience, if you can go to slido.com and type in a question or two, that would be great. You can also fill out the poll for the team. And at the end there, you mentioned dust mitigation with a casing and a lid. Have you looked into how to do that or materials for that yet?
Yeah, we're currently in the process of looking into it. We did some research about maybe potential coatings that we could put on there as well, but there wasn't any like substantial result. So yeah, we're kind of still looking into it.
Okay, good. And when you're doing your loads, is that an earth load? Is that a moon load? How do you handle the gravity difference?
We accommodated due to the moon's gravity, so we changed everything to be in like the accommodating for the lunar gravity rather than the Earth gravity.
It made our safety factor a lot greater as well, so we're able to thin down our design if needed.
Okay, and is that going to affect your testing here on Earth then? If your safety factors designed for the moon, but you're testing on Earth, how will that affect it?
Yeah, we've considered that. That's why we've been trying to do virtual simulations in SolidWorks, but we have not yet tackled how we'll deal with that.
Okay, we have a question here. It says, are you familiar with Astromast? And is it one of the options you considered?
I don't think we're familiar with Astromast. We saw this deployable boom structure that was already utilized by NASA. It seemed like really good tech, but we weren't able to get our hands on that. We emailed a company that manufactures them, but we're not sure if that's like public information, so we weren't able to get that.
Okay, and you've turned in your project proposal, right? Oh wait, yeah. What is your biggest challenge in this project so far this year?
Liseth, you want to answer that?
So I guess one of our biggest challenges, or as of now, is like kind of handling the simulations. We haven't had a lot of experience in it, so we're still trying to like figure out like how to like run these through SolidWorks, to have a better visual of how this is gonna, work in the moon and during launch and all that.
I would say another challenge has also been the online learning. We've been in online school for the past 2 years, so it's kind of jarring getting back in the flow of in-person learning. So we've also had to deal with that struggle along the way.
Well, good. Thank you for the project and thank you for the presentation.
Yeah, no problem.
Okay, we are going to take a break. That concludes session 1. We will come back at 2:10 with session 2, and we'll have UNT, UT Tyler, and Lone Star College at that time. We'll see you in about 10 minutes. Welcome back to session 2 of the Texas Space Grant Consortium Design Challenge Showcase. We have 3 teams in this session: UNT, UT Tyler, and Lone Star College. First up is going to be UNT Team HDS. And you are all here. Excellent. All right.
Hi.
Okay. Take it away when you're ready.
Awesome. All right. As you said, we are Team HDS. My name is Chris Hersberg. I'm the team lead for the Machine Learning Human Interface System.
My name is Elmer Dufresne, and I am software lead for our system.
And my name is Jordan Schraub, and I'm a helper. So first, you might want to know, why are we designing the Machine Learning Human Computer Interface System, or MHIS for short? So when we have missions that go into space, deeper and deeper to the moon, Mars, or beyond, the speed of light suddenly doesn't seem so fast anymore as communication delays increase, become minutes, maybe even an hour or more. And so when astronauts need help back at mission control, it can take a very long time for them to get the assistance that they need. If they're having issues, maybe there's just stress, they're slowing down, and it's really hard to actually identify that when there's such long communication delays. So there needs to be some sort of system in place that actually allows the astronauts to get assistance when they need it, as well as to actually monitor their performance and detect any degradation in order to safely assist them in successfully completing their mission.
So the goals of our project are to show the viability of the machine learning human interface system by, one, designing an application to simulate potential hazards that may be encountered in space, and gather performance data based on human interaction with the application, and implement machine learning to help identify degraded performance, and then assist the user in successfully completing the task. So the way we designed our project was to break it up into 2 modules that are interfaced through a central graphical user interface, GUI for short. The first module is a fire suppression and damage control system, and the second one is an object avoidance system. So the FSDC system will be used to identify the occurrence of a fire, indicate the user location of the fire, and assist the user in following procedures for responding to the fire. The second one, the OA system, will detect an object that are in close proximity to the module within a certain distance and assist the user in avoiding the object, and if necessary, avoid the object without user input.
So for implementation, everything's going to be controlled through a central controller. Both the FSDC and the OA systems are connected wirelessly, and then the user can then interface to the touchscreen GUI. And each system will have its own menu, as you'll kind of see in a later slide. Each user will also have their own profile that they will use to log in, and that way we can actually track how they use the subsystems, and we can use their usage metrics later on for machine learning. All that will be stored on a database that is hosted on the central controller. We're using a Postgres database. And again, it has their login information, how they use the system, everything they're going to need to identify the user and apply machine learning so they can interface with the systems. Preliminary results so far. The GUI has been designed and coded. Right now, as you can see, this is just the main menu, but we have the option to switch between different systems as the user desires. The database, again, is also hosted on the central controller, and all the tables have been made. They're just awaiting the integration with the OA and FSDC systems, so we can actually start populating that data.
So for my system, the fire system damage control will be used in the event of a fire within the spacecraft. It will implement machine learning because just in case a user could be under distress whenever there's a fire on their spacecraft, or could possibly have a health issue, maybe your finger is missing, or it's just any other health issue that may be involved with the individual, the machine will be able to select the correct options for the user in case the user is unable to correctly select the option themselves. Currently, my results with this system are just mechanically implemented, such as turning on the light, generating a buzzer speaker, generating an event through Wi-Fi, which is what my system is able to do right now. It can connect through wirelessly to the internet, and then it may also generate an alarm in case the temperature reads a certain degree, and is able to generate a visual alert such as LED light turning on and off.
Hey team, we're having trouble seeing your screen. Can you double check that you're sharing it correctly?
Yes.
Sure, sorry about that.
Thank you for letting us know.
Completely neglected to do that. I apologize. Are you able to see it now?
Yes, yeah, continue. Thank you.
Yes, we got it under control. Thank you, Matt.
Moving on.
So for the OA system, we're currently using multiple ultrasonic sensors to detect potentially hazardous objects that are connected to a Raspberry Pi unit that use 3 to 5 volts to be powered and have a viewing angle of about 15 degrees for a range of 2 centimeters to 450 centimeters. The camera is currently mounted on a pair of servos that will allow the user to simulate avoiding the object by entering commands to the GUI system. One servo will turn on the X-Y axis, one will turn on the X-axis, one will turn on the Y-axis. And machine learning will be implemented to the machine learning will be implemented to the OA system with the intent of teaching the system to autonomously avoid objects in the event of crew not responding fast enough to an oncoming object. So for the preliminary results, I currently have programmed and tested each sensor to be able to detect an object within a set range. Currently, it is between 10 centimeters and 25 centimeters, just for the sake of testing. The pictures on the left show the object at a certain distance, and the output is shown on the right. As you can see in the second picture, the object has gotten a lot closer, and the output has shown that it has reached a certain threshold where an alert message has been notified to the user. So for this, I currently have the camera running. As you can see, it's moving a little bit forward, getting closer to the ultrasonic sensor. And on the bottom left, you can see the sensors are outputting the data at about a 0.5 second interval. And when the object is reaching a little bit closer, within that 7.5 centimeters, the message has been given multiple times. And it's just showing the object moving a little bit further away, not displaying those alerts anymore.
So here we have our schedule. This semester is mostly over. We are a 2-semester project. This semester, the early part was spent mostly drafting our documents and planning out our diagrams. That's all done. We have ordered all of our parts, and we've begun working on our individual systems. Starting next semester, we plan to have everything completed as far as the individual systems are concerned. We will begin integrating all the systems together, and then we will start our machine learning, and we hope to have that completed by March 24th, giving us some wiggle room to troubleshoot and handle any issues that may come up and be done by May 7th. So in conclusion, the progress so far is we have, again, all our diagrams and documents have been drafted, they're completed. The system's GUI has been designed and has been coded. All of our parts have been received, and we're just in the progress of actually putting them all together. And the only things we have left after that is to actually integrate the systems and then begin the actual machine learning implementation. We would like to thank NASA, of course, for sponsoring this project, and Dr. Timothy Irvin from the TSGC, University of North Texas, our school, for providing us with the opportunity to work on this project. Our professor, Dr. Robin, for his dedicated leadership and membership. He's been a great teacher to us over many semesters, not just for this project. Our lab manager, Alejandro Olvera, who's the guy to go to, gets things done for us. And of course, all of our friends and family who have just been patient with us as we work really hard to get everything done and finish our degree. Here are some references that we put together that we've used in designing our project. And the presentation is now over. Thank you for listening. We are now open to questions.
All right, thank you very much, team. Let me go ahead and share the screen again. Okay, So audience, yeah, please go to slido.com. You can vote in the poll for the team and ask questions and upvote questions. So first, let me ask, obviously you are in person and together. How's it been adapting to that again?
I think it's actually been much better. It's nice to actually go to classes in person and engage with our professors.
Oh, it's just been really beneficial, especially for senior design, being able to work together, having dedicated times to be working rather than trying to get our schedules to work together outside of the classroom.
I personally really enjoyed it, and I noticed kind of like a shift in my grades whenever we were all online. It was very difficult to stay interactive with my classes. As a student athlete, it did help me be on the move a whole bunch, but I wasn't able to really dive into any of my really really involved classes because it was online. Just being in person, I just learned better that way.
Well, good. Glad to see you all in person together. Hopefully all the schools will get to do that, and we'll have our design challenge showcase in person in 2022. So let me ask another question here. You mentioned training systems for next semester. How are you going to do that?
So far, we've mostly been doing our focus on the actual physical application. We've done a bit of research. Like I said, I chose my Postgres database off of some documents I read on the website. It's supposed to be really good to help streamlining the actual learning, but we haven't dove in too deep as far as to how we're actually going to implement the algorithms just yet.
Yeah, so there's two different methods to actually design the algorithms. There's the machine learning, there's deep learning, there's another type of learning that I just can't remember. Well, there's AI, machine learning, deep learning. Right now we're using machine learning, and machine learning can be learned through unsupervised learning and supervised learning. So we're going to be more on the unsupervised learning because we're not going to actually be coding the responses or coding the hard data for the machine to learn. The machine needs to take the information from the sensors and then eventually be plotted in a graph or plotted in a table, and then eventually to be organized, and we'll teach a system to predict based off that data and information.
Okay, very good. And let me ask another question. So how far do you think this can go? I mean, people think machine learning, they think of, say, HAL from 2001, the computer helping them, but taking over. Yeah. What are your thoughts on the future and the ethics of this technology?
I guess I'll start. I really do think AI machine learning is technology is going towards. I mean, we're starting to see it a little bit every day. I know people that use it in marketing to find how data can be worked with. I mean, I'm sure everyone sees Teslas on the road that kind of implement it for self-driving. So the ethics portion, I think we've yet to really hit a huge boundary with that. But it's going to be exciting to see where it goes and kind of what it brings with it.
I would say to add to the ethics of it, I mean, I think with any major technology, it's more about just how it's applied. When you have nuclear energy, it can be potentially, if used right without disasters, it can be a great thing, but it also has the power for great destruction. I mean, it's kind of like an extreme example, but same thing with artificial intelligence. You can use that to data mine and manipulate media or whatever you want to do, or you can use it to help assist people's lives and make it better. So it's really about how it's applied. It's not the technology itself.
Okay, and you've got a little robot on your patch here.
It's courtesy of El-Marie here. She's the artist.
You're the artist?
I did a little bit back in the day. Took some art school in high school.
Okay, very good. And so the robot is thinking that's the idea behind it?
Yeah, so the robot will think about the data that it's been given and then eventually be able to, make predictions on what our machines need to do. So for example, my system, I think that what I would do is whenever the user selects an option from the GUI, from Chris's GUI, we'll be able to see how long it takes for the person to select another option. So we'll focus on time, say that I may be using the system faster than another person. The system could be able to predict, oh, it's El Marie working with the system, or someone slower and be like, oh, this is person B using the system. And then it might be like, okay, person A is using the system, but they're going a little bit slower. Maybe person A is distressed. There's a fire right now. Can't have someone to be in distress. The machine will predict and be like, I'm going to pick these options for you and handle the fire because you're unable to because of whatever reasons.
Thanks for not saying names.
All right, excellent. Well, look forward to next semester. Thank you very much.
Thank you very much for your time.
Our next team is from the University of Texas at Tyler. It is Team Solis. The other half, if you turned in yesterday, we had San Jacinto College talking about this project from the theoretical point of view. And now we have the other half from Team Solis. Are you ready, Team Solis?
Yes, we are.
All right, go ahead and screen share. Take it away.
Thank you for joining. This is Team Solis, and our entry for the TSGC Design Challenge for Fall 2021 is the TDC 73 Novel Non-Tracking Fiber Optic Solar Concentrator for Extraterrestrial Applications. Faculty Advisor Dr. Seren Maloney and NASA mentors Mr. Christopher N. Mendel and Mr. Houston Green. The team members are Jonathan Johnston, Victor Ortiz, Christopher Contreras, Muhammad Wahid, and Deval Patel. Our presentation will follow this outline, starting with the team roles, background, and objective, followed by the specifications of design, material list, then the fabrication process, test bench, and conclude with future work. A Fresnel lens and a collector are being designed to be used as a solar concentrator that have no moving parts on the south pole of the moon to power equipment. Lunar dust and varying temperatures of 40 Kelvin to 400 Kelvin on the lunar surface can hinder performance of the lens. Materials for the lens and collectors that can withstand the lunar environment and transmit sun rays are selected. To protect the lens from the lunar dust, a coating will also be selected. For this project, the teams involved are Team Hyperion, whose roles are to design the dimensions of the lenses and collectors, simulate the lenses and collectors for optical and thermosolar flux in both lunar and Earth environments. Test prototype for optical solar flux to validate the simulation. For Team Solis, material and coating selection for lenses and collectors. Fabrication of lenses and collectors. Fabricate the testing bench and test prototype for thermosolar flux to validate the simulation.
The concept for a Fresnel lens acting as a solar concentrator in this project can be shown in the figure. Here it is shown that the sun rays pass through the Fresnel lens and are converging to a focal point. Using the concept mentioned earlier, a Fresnel lens can be designed where a cylindrical form factor can take advantage of ambient light on all sides, as shown on the left image of a non-tracking cylindrical Fresnel lens, being used to concentrate sun rays onto a collector. The collector then transmits the sun rays by funneling the energy to exit out of its port. This design is what is ideal to be placed on the lunar surface to concentrate solar energy. However, to simplify this process in simulation and prototyping analysis, the design is to only have a 30-degree revolve piece of the lens. This design will allow the simulation to run at optimal levels, while also allowing for prototyping on the lens to be within the means of our manufacturing capabilities. The following image is an optical EM simulation ran by Team Hyperion of a Fresnel lens where sun rays are hitting one end of the lens and coming out the other, and converging to the focal point. The simulations being done are to be validated with Team Solis's prototype lenses by testing them in similar configurations as shown in the simulation. For our objectives, Team Solis will go through the following: material and coating selection that can withstand the lunar environment. fabrication of lenses and collectors by producing two sets of two lenses and a collector from selected materials. Afterwards, polish all the lenses and collectors that have been fabricated, and then apply a selected coating to one lens from each material set. The next objective is to fabricate a testing bench that can hold both the lens and collector in position to mimic the simulation. For our specifications, the first specification is a melting point of selected lenses and collectors that will need to be at least 400 degrees Kelvin due to the high temperatures of the moon. Furthermore, the material of the lens and collector must have a refractive index close to 1.4 to collect most of the sunlight, and it is imperative that the materials have a high transmittance factor of at least 80% since the sunlight needs to be transmitted to create energy. Finally, the design of the lens and collector must withstand at least 9 Gs to survive a rocket launch. Similarly, our coating will also need to have the same melting point, transmittance, and refractive index criteria.
Here we have a list of materials that was provided by last semester's team, which falls under our criteria and are available in Optica EM software. Our team decided on the two materials highlighted in red, polycarbonate and polymethyl methacrylate, otherwise known as PMMA. These were chosen based on refractive index and transmittance and melting point, as well as availability and manufacturability. The lens will need a coating to protect from abrasive lunar dust, which will degrade the lens and decrease optical performance. Our teams researched and compiled a list of coatings that meet the criteria mentioned earlier. We chose silicon dioxide due to being able to be simulated in Optica EM, its market availability, and being able to process and be able to safe environment. For our fabrication method, we chose to machine our lenses and collectors. A 2-inch thick sheet of polycarbonate and PMMA were selected. These sheets are thick enough for our prescribed dimensions of lenses and collectors to be produced. A CNC machine will be used to mill our selected sheets of material to fabricate our lenses and collectors. This method was chosen for manufacturing cost and precision compared to other methods. A CNC machine will be used to mill, and also in the figure we see that produce the two lenses and a collector from each material.
After the CNC process, the lenses and collector will need to be polished. The reason why they must be polished is to ensure that there are no scratches or imperfections from the CNC machine process that can interfere with the clarity and light transmissibility when testing both lenses and collector. Therefore, a paste compound polishing method is being chosen since this method can be applied to both PMMA and polycarbonate materials that will increase the surface finish and smoothness as shown in the figure. As stated previously, the coating for our selected lenses is going to be silicon dioxide. The coating attributes are that it repels lunar dust, has a high melting point of 1900 degrees Kelvin, and a high refractive index of 1.45. It is also able to block high radiation as well. To measure the coating, a thickness gauge as shown in the image on the right will be used to measure the coating thickness of the lens.
We have designed a test bench that mimics the simulation in terms of position for the lenses and collectors, where light will pass through the lens and focus on the collector. The test bench has a revolving shade that shields the collector from ambient light, which eliminates a factor when assessing the lens's performance. The test bench has a pivot armature that can raise and lower the lens to have its focal point line up with the collector's center. The pivot armature also rotates with the cylindrical shade to point the lens towards the sun. For our future work, it will be consisting of testing thermal concentration and comparing the thermal simulation results for validation. For our testing, we will have placed the following thermocouple devices as shown in the figure on the right. Similarly, the simulation will have readings in the same region for comparison. Then, using the thermal output of the collector, we can determine the amount of solar heat flux energy that has been produced once the lens has concentrated that energy. This is the bill of materials for our fabrication of the lenses and collectors and testing bench components. as well as the safety wear we will use when conducting our testing. Our group participated in doing outreach where our University of Texas at Tyler hosted the A-Leaf windmill competition. Our members were assessing the windmills for performance. We would like to thank Dr. Soren Maloney, our faculty advisor, Dr. Andreas Garcia, our University of Texas Tyler Houston Engineering Center Director, Mr. Christopher N. Mendel, Mr. Houston Green, NASA mentors, Jacobs Technology, and TSGC for sponsoring this event, as well as Team Hyperion, who had collaborated with us, and Dr. Nathaniel Wiggins, who also was part of San Jacinto's engineering. Here are references that we used for our presentation. Thank you.
Okay, thank you very much, team. Audience, please go to slido.com. You can go there to ask questions, to upvote questions, and answer our poll. Here we go. Okay. There's the app at the bottom there, slido.com. Use code TSGC 2021 to get inside, and then you can answer questions, ask questions, and fill out the poll. All right. So team, you talked about the 30% section that you're going to create as the prototype. Can you just take your results and multiply by 12 then, or what do you think are the factors with just doing one section?
So for our analysis, we simplified it to a 30-degree section. It wouldn't necessarily be multiplying by 12. That would be like the most optimal way if the sun was actually shining all the way around. But on the moon, we would actually know the section that would be most likely shined upon. So if it were a 120-degree cutout that was actually being shined, and then the rest was from ambient light, such as earth shine and the emissivity from the moon, we would then take that into consideration.
Okay, thank you. Thank you. We have a question here. Who will write the code for the CNC machine?
Yes, we have a machinist that we're going to write a code in a program called GibbsCam, and they'll be advising us to help us do it. It'll be a 3-axis CNC machine that we'll be using.
And I noticed on your materials list there, that part I think is pretty expensive for the main part of the lens.
Yeah.
Yeah, so you can only do this once, correct?
Essentially.
All right. So definitely take care with that machining.
Correct. We do have some extra material of PMMA, and that's for that reason.
How has it been working with a team from another university?
I would say it's been pretty interesting because we kind of now have the idea of how branches would work, similar to, I believe, Christopher and Mandela and Houston Green were also explaining how this would be how you would have it at NASA, where you would have one group in charge of material selection and analysis, whereas another would be doing simulation and prototyping. So it gives us some insight of just the interlinkings of multiple groups working in tandem.
That's a great experience. Yeah, I'm glad the team's got to experience that. So what's been your biggest challenge so far?
I would say acquisition of materials and finding, being able to, finding a machinist and getting that down for actual prototyping. That would be the most challenging thing because of the supply chain issues.
All right. Any other last minute questions from online? If not, Thank you, team, and good luck next semester.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Our next team is Lone Star College Sci-Fair, Team Silas. And they are a multidisciplinary team from many different majors. Do we have them all on? 1, 2, 3, 4, 5. All right, Team Silas, are you ready to go? All right, go ahead and share and begin when you're ready.
Hello, everyone. My name is John Lentz, and I am joined today by Min Thu Nguyen, Alma Gallardo, Melanie Berg, and Marcelo Carazelas. We are dual participating in NASA's Micro-G Next Challenge and TSGC's Design Challenge. This is our presentation.
So, through the Artemis program, NASA is sending the first woman and person of color to the moon, while furthering their endeavors towards future missions on Mars. In order to prepare for this, NASA wants to update their anchoring device. This challenge is critical because not only will it bring us one step closer towards exploration on Mars, but it also is a big leap towards the representation of women and people of color. Moreover, NASA is looking for an anchoring device which is portable and can be used manually and is easy to use in order to explore underneath the ice-covered surface of celestial bodies. Next slide, please. For these reasons, Team Silas has taken up the challenge with the objective of designing a reusable device which can anchor onto rocks on the lunar surface to assist NASA's astronauts in exploring the icy south pole of the moon. Next slide, please. Team Silas sought out inspiration for this device and came across the Microspine Gripper, which utilizes its 16 carriers independently with 12 microspines each to latch onto the multilateral surfaces of rocks. This device, which has been designed by JPL NASA in 2011, had never been used, but it had been tested and designed to grip onto the surfaces and drill onto them. Team Silas seeks to utilize the inspiration from this design to create a new device, which utilizes microspines with stronger holding strength without needing to rely onto any form of penetration to avoid damaging the surfaces of the samples collected. Moreover, Team Silas has also taken a look at the Freeclimber Lemur 3, which had been also designed by NASA and was utilized for terrain exploration and utilizes a similar gripping mechanism like that of the Microspine Gripper. With its thousands of hooks, it latches onto the rough surfaces of rocks. Team Silas is drawing inspiration from this design technology to create an anchoring device which is easily portable in size and weight while maintaining or even improving its efficiency. Next slide, please. Through the engineering design process, Team Silas has and is addressing the design criteria provided by NASA Micro-G throughout the development of this device. As shown in the slides, Team Silas seeks to develop a device which is adaptable to the different rock types, cannot penetrate the surfaces of the rocks, but however, it can mildly scratch them, is operable with 1 or 2 gloved hands. The device must have a 10-pound holding force and have a dry weight of less than 5 pounds earth weight. The device must also be adaptable to the icy surfaces since the temperature in the lunar surface is very cold, which creates an icy layer around the rocks. The device must also be storable within a 6-inch diameter by 18 high-inch cylinder. And we will also be addressing to minimize the pinch points as much as possible.
Thank you, Marcelo. So after reviewing our research as well as the design criteria made based on NASA requirements, the team proceeded to come up with preliminary designs. We came up with Grabber and Argo, which stands for Apparatus for Rock Gripping Operations. Structurally, the two designs are very similar in 2 ways. One, the design both have segmented limbs, which help with either extending or contracting and grabbing onto rocks of many types of surfaces. In addition, the two designs have, or rather the design limbs have microspines, which help strengthen the gripping onto the rock. The designs, however, are different mechanically. Right. Grapper relies solely on these crisscross structures located on its limb in order to be fully functional. Argo, on the other hand, has a cable system as well as torsion springs that significantly help with applying force, grabbing, and gripping onto rocks. And please note that later in this presentation, we will show you a better view of the cable system as well as the torsion spring to give you a better idea of our design. After coming up with the preliminary designs, the team proceeded to compare our designs to select the one that we would like to continue working and improving on. Since the Microspine Gripper was one design that we drew inspiration from, we decided to use it as our datum and compare Grapper and Argo against it. Now, in terms of anchoring ability and holding strength, Grapper underperformances compared to our datum. Argo, on the other hand, meets and exceeds the features of our datum, and it also earned a much higher score compared to Grapper. Therefore, we decided to move forward with Argo.
The Argo design is a compact lunar anchoring device weighing 3.7 pounds as calculated by our SolidWorks software. It is 17 inches high and 5 inches in diameter in its resting position, reaching a maximum of 13 inches in diameter when being operated. The design consists of 5 segmental limbs kept in constant downward force through the use of torsion springs at the base of each limb. The limbs will be raised to their anchoring position by compressing the handles of the outer ring and the central ring together. Each of the limb segments contains 4 independently actuated spines that are designed to lodge into defects on the rock surface with only mild scratching, which is allowed per the Micro-G challenge. Next slide. This is a better image of the cable system along with our torsion springs. The spines are locked in place with the force provided by a linear ratcheting system connected to a cable system going from the outermost segment of the limbs and into the bottom of the central housing. Next slide. The tension will be kept on the limbs as the astronaut extends the topmost handle upward, contracting the cables going through the system, providing a gripping force much like the end of a finger. Next slide. On the left is the Argo device in its resting position. To operate the device, the handles of the central housing and the outer ring are compressed, raising the limbs against the downward portion of torsion springs, resulting in the middle image. The device is then placed against the rock surface, and the limbs are released from their holding position, contouring to the surface. After which the handles on the top of the device is extended, contracting the cable system, thus causing the spines and limbs to grip the surface, allowing the device to anchor onto both flat and curved icy surfaces. Next slide.
The team has made a small-scale mock-up of the Argo design to test proof of concept. By designing the smaller scaled mock-up, the team was able to gain a stronger understanding on how the limbs should interact in the model and visualize the cable system within this design. This mock-up has given the team insight into how the Argo design could be multifunctional for picking up smaller rocks on the lunar surface. Did I just cut out? Sorry. I'm sorry, here we go. Okay, this mockup has given the team insight in how the Argo design could be multifunctional for picking up smaller rocks on the lunar surface in addition to anchoring, exceeding the requirements given by NASA. Moving forward, the team will be 3D printing several prototypes for reiterations to improve the design. The team will be addressing in future work the possibility of pinch points.
We will be addressing the possibility of pinch points and of dust tolerancy. The material that we have chosen to manufacture the device out of will be aluminum 6061 for the body and stainless steel for the cable. Next slide, please.
The team has gone through the stages of brainstorming ideas and evaluating preliminary designs to choose a design that can best accommodate the challenges presented by Micro-G. Team Silas was successfully able to create the Grabber as well as Argo based on NASA's design requirements. The latter meets and exceeds many of the requirements given, so the team has decided to move forward with Argo. This design does not only function for anchoring, but can also be utilized as a picking up device. The team looks forward to manufacturing a fully functional prototype and further testing it at NASA Neutral Buoyancy Lab. Next slide, please. Team Silas will have 3 opportunities for outreach this semester. For the first one, Team Silas has partnered with Harris County Public Library to create a video about NASA's Artemis missions and the moon. The purpose of this video was to teach the young audience the impact of Artemis mission and the different moon phases with an engaging activity with Oreo cookies. In the future, the team will also have the opportunity to work with Cub Scouts. The team will work with around 20 scouts in December 4th. This 2-hour event will consist of a brief presentation of an overview on NASA missions and a hands-on activity that will engage them in the design process. Finally, Team Silas plans to present the project at the Honors College Undergraduate Research Conference in December 10th. The team will share their project with undergraduate students to inspire them to be part of future engineering projects presented by NASA. Next slide, please. Many thanks to TSGC for giving us the opportunity to pursue aerospace engineering, and special thanks to Dr. Urban and our faculty advisor, Dr. Wang. Thank you for listening to us, and we'll leave it open to questions.
Okay, thank you very much, team. For those online, go ahead and go to slido.com, please. Use the code TSGC 2021 to log in there, and you'll be able to ask questions, upvote questions, and answer the poll. Poll is open now. Okay. So we have several questions here already. So first question is, what's the practical use of the device? If it only picks up 10 pounds, that's only 3 pounds of moon weight. Can they just pick up rocks like Apollo?
So NASA wants the design to be able to anchor their astronauts from two rocks on the surface, but they also wanted to have a dual purpose of being able to pick up rocks as well. So per the requirements, we are given 10 pounds of earthquake holding force, and that is to be able to anchor their tools as of right now, but the designs have to leave room to be able to be modified to maybe hold more weight for the missions.
Okay, next question. The handle seems very big. Will the astronaut be able to grip it with a single hand with a spacesuit on?
Yes, the handle of the device is 3 inches in diameter, which we measured should be able to be held by the astronaut's club hand. We are going to work during our testing in order to with ski glove to see how that works out, and we will make modifications as necessary. But as preliminary measured, it should be able to be held by the astronaut.
Okay, next question. How do you plan on testing for the durability of the entire device when the time comes?
We'll be making a 3D printed model of the device, and we will be testing that on various rock surfaces. We will also be testing other materials in order to see how the device holds up to that, and we will make changes as necessary in the coming semester.
Are you going to test that for dust tolerance as well?
We will be testing for dust tolerance. So this design is primarily going to be tested in the NBL. However, we would like our design to be able to withstand the lunar dust, which, as we all know, is a big problem. And we will be doing further research on that in the coming semester. As of now, the device operates with very minimal rubbing pieces. So we've tried to minimize them, though we will be improving on any other areas.
Okay, next question. Were safety precautions considered with the teeth located on the interior of the appendages? Is there any potential for them to cut or puncture the astronaut suit?
Yes, so the pinch points from the spines are a big concern. We are currently working on making them retractable for transportation of the device. So using that interior cable system. So we will, either we want to make them retractable or we are working on also devising a cover for them so that the astronaut is not in any danger of having their suit punctured when operating it.
Okay, great. Thank you very much, team, and good luck.
Thank
you.
Thank you, Dr. Irving.
Thank you.
Okay, this concludes session 2. We're going to take a 10-minute break and come back at 3:05. We'll see you then. Good afternoon, everyone. Welcome back to session 3 of the Design Challenge. We have 3 teams coming up in this session: Houston Community College Team Eagle, UT Tyler HEC 5, and University of Houston Team Red. So first up is going to be Houston Community College Team Eagle. And I believe they are all online. And are you ready to go? All right, thumbs up. So go ahead and share the screen.
Good afternoon, everyone. My name is Cyrus Abbasi. I'm the Communication Officer and Principal Investigator for Team Eagle, representing for the first time the Houston Community College for TSGC NASA Design Challenge in the initial Mars Habitat category. I would like to express a special thank you to everybody involved in gathering and granting all of us the opportunity to apply our learning into practical applications. Without any further ado, I would like to introduce my teammates, starting with Brian Hurtado, who is the team lead and fabrication specialist, Yasemin Soltani, team scheduler for design timeline, and Talha Eftikhar, who is responsible for the software applications of the design and team project submissions.
So the TSGC Initial Mars-based topic challenges teams to engineer an innovative piece of technology that will aid in mission-critical aspects for the first habitat that will be developed for the Red Planet. Based on the objectives and guidelines of the Initial Mars Design Challenge, parameters such as a significant reduction in mass and volume consumption, mission cost efficiency, reduction in manufacturing time and complexity, and design simplicity became the team's primary goals to achieve. With these factors in mind, we challenged ourselves to create the main portion of our design with a single part, allowing it to fulfill the parameters of being lightweight and volume efficient, while also being fast and simple to manufacture. This was achieved by utilizing origami. Now, a little bit about origami. Origami is the Japanese art of folding paper into decorative shapes and figures. Depending on the folding patterns or the material used, structures can be folded to deploy automatically or form rigid columns that can support mass. In recent years, origami has had many applications in engineering and design. Its folding capabilities have been utilized by NASA in space exploration, such as in satellites, and it has the capability to significantly reduce volume and mass consumption. The Bedogami design utilizes the Miura-Ori folding pattern for its structural stability, a pattern invented by Japanese astrophysicist Horio Miura. The team chose this pattern for their design due to it utilizing parallelograms to form the tessellation of the forms, making it form a rigid origami, mainly comprised of alternating mountain and valley folds. The simplicity of this folding pattern allows for assembly in a single motion, therefore reducing the amount of manufacturing parts to only a single foldable structure.
The first folding the team made using Miura pattern was made on a regular sheet of paper, which turned out to be extremely resistant and capable of holding a calculus book of over 1,300 pages. The team then moved to develop an upscale prototype of paper, which was essential to the team to gain familiarity with the folding process. Once acquired better knowledge on folding and origami from the upscale version, the team proceeded to apply the folding onto the desired materials, leading to a final prototype made of heavy weighted paper of 49 grams, which was then used for the testing process. This is a visualization of how the Bedogami would look like once expanded. And this is a visual representation of how the Bedogami look like when contracted. Throughout the development of the Bedogami, the team conducted several strength tests on each prototype of the design using mass objects ranging from heavy textbooks to rice bags and detergent bottles to the compressive strength test machine at the UT Tyler Mechanical Engineering Lab.
To calculate the stress with the elastic limit of a origami, we use Hooke's law. We conducted 4 tests for our design, 2 for calibration and 2 for our data collection. The origami in a structure test is half of the size of the test sample number 2. The sample number 2 is a full-size prototype and is a test overview shown on this diagram. In this image, we measure the total area of the mechanism compression machine. The way we conducted a stress test and a strain curves, we briefly evaluate the effects of angle variation on the mechanical properties. For example, on test number 1, our raw data is graph were obtained from the compression test. Indicated at a force of 620 newtons with a calculation for the stress yield was 87,000 and with an elasticity of 241,000 pascals. As well for a second test for the data collected. Test number 2 indicated a force of 990 newtons with a yield stress of 13,000 pascals with an elasticity of 21,000 pascals.
We believe the future of our project to be fruitful. As we near the end of the semester, our team and fabrication personnel have already started the implementation of new variant of the folding pattern, and we have also plans to venture into realm of compliant mechanisms to integrate them into our design. Our team is also working on different applications of our product, and most importantly, the concept itself, to serve the good of humankind. Applications such as disaster-stricken areas in need of shelter and beds and field hospitals are only 2 examples where light-weighted structures that are deployable from such small volumes can play a major role in emergency operations. This is our new variant that has 3 times the height and 3 times the load capacity compared to our very first small prototype. Just incredible. Our project and proposed concept brings tremendous amounts of savings for future NASA missions, not only to Mars, but even for Artemis missions coming up. We visualize the habitat quarters as seen in this concept 3D model, where we saw best fit for all HABs utility to be based at a central column within the module. Usable space becomes very restricted when furniture such as beds and the HAB are unretractable. But with implementation of Origami, our design allows for twice usable space that can be utilized for other means. Due to the retractable nature of our design, our beds are safer and easier to launch in the fairing of rockets, as they can be secured much better due to their lightweight and shape. This allows for transportation of more equipment in a single launch, dramatically reducing cost in both launch vehicle and module design, manufacturing time, manpower, overheads, parts, testing, certification costs, mounting, and fuel, delivering our initial proposed goal of dramatically cutting costs by means of volume and mass. We achieve all our objectives by implementing Origami to reduce mass and volume, eliminating multiple launches needed to ship the excess mass originally, creating a simple design that assembles and deploys easily, and it is tailored to every astronaut's physiology. To make space exploration cheaper and accessible, as to feed the explorer and pioneer nature of our species to go beyond. Thank you.
All right, very good. Thank you, team. So audience, if you would like to ask the team a question, please go to slido.com, enter the code TSGC 2021, and you'll be able to ask questions, upvote questions, and fill out the poll as well. All All right, let me ask a question first. So you mentioned a couple times that you would tailor this to each inhabitant. How would that be done and why, I guess?
We saw it fit for the comfort of the astronauts to go that route. This will be something that we'll actually explore more going to the second semester. Essentially, we wanted to also put the fatigue aspect of the mission, if not getting enough sleep during night because of the uncomfortable situation that a bed can cause, could also reach out to the safety issue of the critical mission aspects that need to be achieved. So we looked at it as a safety kind of a measure to try to mitigate.
So in terms of tailoring, would that be like the number of folds or the size, or how would you tailor it?
Yes, so the structure of the origami, when folding, essentially you can fold the certain parts of the structure to different heights. So you can actually, by measuring the physiology of the astronauts, we can actually make the bed itself have a kind of a fit shape for the astronauts. So when they sleep on it, actually, it kind of holds.
Interesting. Have you looked at what kind of materials you would be making this out of? I'm guessing not paper, right?
Well, right now it is paper. We're looking into possible polyethylene structures and materials. We are also, as mentioned in the presentation, looking into going the route of compliant mechanisms. So we're open to different materials, but for now we've been venturing more into paper to see how that turns out and how we can get the concept structured.
Okay, and do you think there are other applications for construction of a Mars base that this could apply to?
Yes. So the initial idea was that when we ventured into the origami, we wanted to simplify the problem. So we picked the most simple geometric shape we could, which was a cubic rectangle, and hence a bed. But this is not limited to a bed. We actually already have been in our meetings, we've been conversing and brainstorming about where else we can implement this thing. And one of the main areas that team members really wanted to do activities around was also applications on Earth for rural areas and hospitals. And when field hospitals need to be deployed, these things are really lightweight and all that stuff.
Oh, very interesting. That would be great. Yeah. All right, we have a question online here. So in the past, mass from object carried into space have been used to protect astronauts from space radiation. Have you considered this?
I couldn't hear you. I think you broke off.
Okay, so it says in the past, the mass from objects carried into space have been used to protect astronauts from space radiation. Have you considered this?
So yes, we did at the beginning. Our goal was to, when we did the brainstorming to figure out which was the challenge that we could have dived into, we looked into radiation shielding and we thought about different ways to protect astronauts from radiations. We also thought about implementing the origami pattern structure to a possible shielding for the base. But yeah, it's definitely something that we're gonna look into.
All right, good. And all right, last question. So who's got the drone that made the video that you did? That was a neat way to end it. Yeah, very nice video.
That was my thank you.
All right, well, great presentation. Thank you very much, team. Good luck next semester.
Thank you, everyone.
Thank you.
Thank you.
Thank you.
Our next team is from the University of Texas at Tyler. It's the team HEC 5, and we'll make sure they're all online. Audience, as you watch, feel free to go ahead and ask questions online. Use the code TSGC 2021 in the slido.com app. All right, team HEC 5, are you ready? All right, take it away.
Bigger. Make it bigger. Okay. We are ready. Give me 1 second. My background, my video. Okay, perfect. Okay, perfect. We are ready. Everybody's ready?
We are ready. Go for it.
Good afternoon. My name is Juan Pablo, and we are Tyler Group 5. Our group is composed by Juan Pablo, myself, Abdul, Ingrid, and Kowa. And today we are presenting Vehicle Interchangeable Electronic Controller Network System. The presentation today will be based on 5 points: background, objective, requirements, project design, preliminary results, goals, and future work. Backgrounds. Project background is based on the following aspect: logistical aspect. For any NASA mission, providing a spare component to the spacecraft is very serious task. Therefore, logical aspects are a key to consider. Timeline replacement. The duration of the changing of replacing a failed system might affect the mission goal. Increase flexibility. The importance of expanding the system tasks performing that can help to achieve the mission goal. Our objective is to develop a proof of concept for vehicle interchangeable electric controller network system that make multi-stacking control system run a vehicle application to support the long duration mission goals using common connectors for easy to be replaced. And the next slide will be presented by my partner Ingrid.
Hi, my name is Ingrid. Our system required a network server that will interact with a different controller. And also on our project, we are going to use a common serial interface that will allow the communication between the different controllers. The system will use 4 different controllers in order to simulate the 4 vehicle applications. The interchangeability controller IC for the exchange of communication from the different application, sensor, and main controller. Also, in our project, we will use a graphical use interface called GUI that could interact with the different controller. And the printed circuit board PCB for the wiring connection. Also, the enclosed for the communication and the connection for the safety purpose. And the last one, the requirement software to make a connection with the IC server and all the application. And my next slide going to Abdul and Kowa. We can hear you, Kwa.
Okay, can you hear me now? Yeah,
Yes.
moving on network system architecture. My name is Kwa and I'm gonna present with Abdul. Our main network system architecture has three main departments from controller system, application, data communication. Take a look on the top level architecture here. We have a server managed for other controller to stimulate the application on the vehicle. Network server on the detail look. So all the controller, main controller and agent controller using one unit. That's one unit, one same kind unit is Arduino Uno. We utilize the printed circuit board design. All the shield available on the marketplace allow us to attach on the top of the unit, give it the convenience way for connection. From there, we can connect the Ethernet network for network communication. Network communication between main controller and agent via the Ethernet using SFTP file transfer protocol. For all connection design, the Arduino is easy to use. We keep that convenient aspect. All the analog, digital, I2C connection gonna use one common connector to plug in, easy to plug in, easy to plug out, and a common power supply, 9-volt batteries for all controller, or a USB port allow operate the controller power supply. Moving on, application. I do. You on mute. For application here, we have we're gonna stimulate 4 application on the vehicle from temperature, acceleration, light, and air pressure. The key aspect to declare the behavior, positional behavior by the dip switch. So setting out a value can declare the positional. From that, we can tell the agent controller to what position. From there, it's going to request the server for appropriate behavior programming. Abdul, you can continue.
Yes, I'm here. My mic was not working. Hi, everyone. My name is Abdul Faruqi. I'm presenting the application part. In this project, we are going to use 4 sensors, which will simulate the 4 vehicle application. This sensor is temperature, light, 3-axis acceleration, and air pressure. Each application has a LED to display the running, stop, fault, connection to the network. We use the dip switch for requesting a suitable behavior from the network server as a potential identification in the printed circuit board. Next slide will represent my partner, Kwa.
The graphical user interface designed to monitor all the status for agent controller on and off. Here our detailed block diagrams. We can start from sensor, contain data, controller gonna go connect into the sensor with a dip switch. So from there, it's gonna connect, communicate to the main controller, declaring position and requesting appropriate programmings. And the server, the main controller, gonna send out the programming for the agent controller to run and perform the task. All the status is going to be displayed on the graphic center. We have a chance to put our design into a markup prototype. So all here is here's our server, and around it is the agent controller, and all the wires we are running underneath with utilize all the common connector just plug in all for all same unit. V.
Thank you, Pa. Hello, everyone. My name is V. Our preliminary experimental results were conducted by simulation on Tinkercad. The code was used to run the sensor system using an Arduino Uno R3 as the main controller. And the LCD screen showed the measurement from each application. The LED indication system is utilized to update the status by receiving data from the agent controller with green and red LED light. So for the first application is the temperature sensor system that used to measure room temperature. The red LED illuminates at the average of 100 degrees Fahrenheit, and green LED illuminates at the average of 75 degrees Fahrenheit after 25 trial testing. The air pressure application detects air quality and measures pressure levels. So when the pressure is moderate or high, the green indication lights up, and when pressure is low, the red indicator turns on. The testing was repeated approximately 30 times. The light induct LED sensor system is used to measure light intensity. The brightness level influences the LED indications. So after around 25 attempts, whenever strong light intensity of 10, green LED turns on, while red LED indicates for dim light. Now I'll pass it to Juan Pablo.
Our future work and plans is to complete the prototype, implement the coding, testing, and make the system. We believe with our knowledge, we make this prototype efficiently and fully functional. Thank you. And also we want to thank the opportunity that we have. They gave us Tim Urban, George, our mentor, Ali Garcia, our faculty advisor, Yasser, our senior design professor, and Andres Garcia, our Houston Engineering Center director. Thank you.
Okay, thank you very much, team. All right, audience, go to slido.com. You can ask them questions. Use the code TSGC 2021 to get into the Design Challenge Slido account. Ask questions, upvote questions, and vote in the poll. See if there are any questions there yet. Not quite yet. So let me ask, you've got 4 different examples: light, acceleration, air pressure, and temperature. So are those the same things you would do for a long duration mission, or do you have other long-term plans?
Those we use for testing purpose on the substation. We want to make sure all the substation agent controller works with the code before we implement it into the network.
Okay, good. And so is it only 4, or could you handle more than 4?
For sure, the design should handle more than 4, but when it's connect into any kind of application, the agent server gonna send a request into the main controller. So from there, any changing from the code to run the new application would be solved. So that yes, it could run in more than 4.
Okay, good. Thank you very much, team. Good luck.
Thanks.
Thank you, sir.
Thank you so much.
Thank you so much.
All right, our final team for the afternoon is going to be the University of Houston, Team Red. We have 5 students, and we'll make sure they are all online and ready. Okay, looks like you're good to go. Are you ready, Team Red? All right, floor is yours.
Okay. Harry, do you mind sharing your screen? Good afternoon, everyone. My name is Humberto Leal, and I'm the team lead of Team Red. We are representing the University of Houston, and these are my teammates.
Hello, everyone. My name is Rogelio Castilla.
Hello, I'm Saloni Mistry.
Hi, I'm Harry Goldberg.
Hello, I'm Celine Cherian.
And also we have Austin Flores, another team member that due to personal circumstances, he wasn't able to make it. In conjunction to Texas Space Gun Consortium, we're also working with participating in the NASA Micro G Next Challenge. And we chose challenge number 1, the sample size location calibration marker. So a little bit of background before we go into our design is NASA plans to go back to the moon in 2024 to the Artemis mission. And part of the mission is to get a better understanding of the lunar surface. And in order to do this, they needed specific devices. And we chose to work on the sample size location marker. Back in the Apollo era, which image you can see on the right, they had a marker that they used to place on the ground. They have a color reference to be able to take pictures of it and identify different geological structures and sample collection and data. Now, that design is really old because we haven't been in the moon in a while. So our team mission is to redesign it. Next. So our design objectives provided by NASA Micro G Next is to design a sample marker for astronauts to deploy on the lunar surface. We want to focus on ease of use, since the astronauts, they have a limited hands dexterity. So some motions with their hands are difficult. So this device, we need to emphasize on ease of use. It cannot be any complex movement or anything like that. Also, due to the pressurized suits, they are not able to bend down. So we need to make our device tall enough. So once they place it on the ground, they don't bend too much or nail all the way down. They also have to be light. Sending things to space is expensive. And also astronauts will be carrying that from time to time. So it needs to be lightweight. It has to be easily visible and recognizable, because sometimes they will leave these markers on site and they need to be able to pick them up and reuse them. And last but not least, this is a requirement that NASA Micro G did not provide us, but the team thought that it was really important to focus on, which is dust tolerant. The lunar surface is a really harsh environment with fine particles of dust that could prevent the mechanism from working. So we also have to focus on our device to be dust tolerant. Next. These are the design specifications as provided by NASA Micro G. I'm not going to go in detail to all of them, but I also need to mention the markers. Then each of them, they need to have a color scale for reference, and they also need to be they can only be manual powered, so no electronics or any kind of mechanisms like that. And they need to be able to stand on an uneven surface. And now that we know about design specification, the background, let's talk about our journey through this process. Next. So now we're going to talk about our preliminary designs that we have for this idea, and then we're going to move on to our final idea. Next.
So the first design that we came up with was a combination between a camera lens and a coffee mug. So we wanted to use the camera lens mechanism as like a locking mechanism for the tripod legs to fall down, whilst also having coffee mug handles to hold the marker itself. One of the pros of this design was that it's safe and it's easy to use. However, we didn't end up picking this design because of the intricate locking mechanism and for it to be like less dust tolerant, which is why we didn't pick this design. Moving on to the next design.
Our next design was the Origami Design. As you'll see in basically every design, one of our key considerations was coming up with a solution to meet the volume restriction, be as small and compact as possible when stowed away and transported. But when in actual use, we'd like to have as much, as large of an object as possible in order to help with moving it and picking it up without, again, having to bend over too much or anything like that. And this really was the best solution for something that expanded to a very large size in relation to its collapse size. Unfortunately, we realized that it wasn't the right solution because it was needlessly complex. It wasn't the right solution for something that withstand its shape and withstand compressive forces. And the solutions to all these problems would create a lot of pinch points, would create a lot of points of failure, would create a lot of areas where dust could settle in where it's not supposed to be. And we realized that it really wasn't the right solution to what we're trying to solve.
Finally, we thought about the tripod design, also called the inverse umbrella. Some of the positive things about this is that we really appreciated the sturdy tripod structure. It is a structure which, in this case, is very good for multi-surface, and it provides a sturdy structure to avoid deformation of any kind, but also to be able to keep the marker up and provide a decent height. The biggest change that they had to the original NASA marker was the fact that it had a locking mechanism to make sure to be able to push the legs and make sure that they stay locked in power to avoid wobbling and things of that issue. The issue that we had is that it was very similar to the existing NASA marker, and in our opinion, the philosophy of our team is simplicity is key. We really want to put ourselves in the boots of the astronaut, and in order to open it, the astronaut would have to literally take their hands, untwist it, use both their hands, and to pick it up, it would just not be as simple as we could optimize it to be. Therefore, we didn't go with it, but we picked out some of the best things of it for our next iteration.
This is how we compared our designs. The mug and tripod designs were simple and safe from folds and sharp edges. However, they were a bit similar to the current sample marker. On the other hand, the origami design is compact and easy to use. However, the manufacturing process includes a complex hinge system, and the design has folds that could potentially trap the fingers, but the folds have a big enough gap to not be considered pinch points. So based on our team's designs, we decided to combine the concepts of each to create SED, which is safe, compact, and easy to use.
Here is an animation of our SED device. As you can see, it only takes a simple twist in order to release the locking mechanism, which allows the legs to go up. Now the legs can move up to 35 degrees, so we ensure that with our hinges. And again, it only takes a simple twist of the handle to be able to lock it up and back into place. So I'll describe the SED device in more detail. Our name is actually Selenological Exploratory Device. We call it SED. I'll be referencing that for shortness. Again, we really tried to go with the model simplicity is key. We had a lot of ideas, especially the origami, but the more complications that there are, simply there are more failure points, and it really is not efficient for the astronaut. Therefore, we tried to take the best points, such as a simple deployment mechanism. As you were able to see in the presentation, it only takes a twist of a handle, and then the device would essentially release itself and almost double its size. Therefore, it's very easy to deploy. And again, it's easy for the astronaut to pick up because it's already in a much bigger form for the astronaut to be able to pick up. So there is that locking mechanism, which we have, and it's almost like a telescoping mechanism. When the handle is twisted, inside it just releases a simple lock that is hard to clog, which is able to expand the device. Also, it is able to stand in surfaces up to 35-degree slope, We debated whether we wanted to lock each leg individually or not. And we just figured that if we set a maximum range of how much it could go, and we set it as 35, it would give us enough space as to meet the requirements of the 20-degree incline that it needs to be able to meet, but also give it a little bit more space in case of any other funnier or harder terrain. It's very convenient because it's sturdy, but it's still adaptable to different surfaces. One of the biggest points is that it's expandable. When it's locked away, it's very, very small. It's 15 inches, fits very well. However, we're able to have this inner rod fit inside of the thicker bottom rod, which is able to almost allow it to double its size. A final thing that I wanted to talk about was the reason why we have a mesh in 2 of the legs. And it is that although when we had solid 3 legs, we were under a pound, we really, really want to consider the interest and conflicts of manufacturing. And it is the fact that we want to reduce weight as much as possible because it is expensive to send things to space, as everyone knows. We want to save as much money as we can. Therefore, we constructed an, I would say, creative mesh, which allowed us to maintain most of the, I would say, very, very good, like up to 80% to 90% of the integrity of a solid leg, while allowing us to reduce the weight by up to 30% while maintaining a durable structure. There you go. So right now, here is a slide of Astronaut, average size Astronaut. We calculate this Astronaut to be 5'9" for reference, 5'9" inch. To his left, you can see an undeployed device. It's on the ground for you to be able to get the reference of how big it is. But of course, this would be very easy and practical to carry. And to the right, there is a deployed form of our device. And as can be seen, the astronaut would have to do minimal movement in the waist. And it also takes very, very little finger dexterity. All they have to do is grip the surface and twist. Another thing that I wanted to talk about was the fact that in one of our legs, we have a solid leg, which allows us to paint our color scheme. We decided to paint and to not go for sticker because of the high temperatures that can be reached, which could melt any material that is thicker. And also there is section, say A1 here. This is our section where we would label each marker for reference. I also want to finally talk about material. We chose aluminum 6061 or 661. We found that this is the alloy which gave us most compromise on, first of all, price for manufacturing, but also ease to manufacture. This is an alloy which has good weldability, and it's usually used in items that are extruded. It's also very resistant to temperature changes, so it will help us prevent deformation and such, while still being a good compromise with weight as well, because this is something that we want to keep as light as possible.
Okay, so to conclude, our device, Rogelio made a wonderful job explaining. We work a lot into this device. We have way too many iterations. We had 6, and we only talk about 3. Our device, and we come up with this solution, which is easy to use, light, less than a pound, compact, dust tolerant, and include all the necessary labels and markers. And furthermore, can be placed on an uneven surface. Now, for future work, we plan to 3D print the prototype and test it to see how it's dust tolerant and how stable it is on uneven surfaces. So we calculate that it will be stable at 35 angle. So we are gonna put it at 35, see if it's stable, if it's double, so why not? As Rogelio mentioned, we're gonna manufacture it out of aluminum 661, which is the best compromise between weight and durability. For next semester, we're going to do a finite element analysis and stress testing to see if our weight, if the measurements that we took to reduce weight are going to be sacrificial to the integrity of the structure as a whole. And last but not least, next semester, we plan to do an outreach event in collaboration with the SIVA, STEM Academy, to talk about the engineering process and we're joining NASA. And that's going to be it. Thank you so much. Any questions?
All right, thank you, team. Got time for a couple short questions, and please fill out the poll. So first question is, so you said you had at least 6 different ideas for design. So how do you believe yours improves the state of the art in this area?
So before, the previous design, the one that NASA had, it was complex to use. So you have to unlock it with your hands, and you have to put your hands where the legs are, and you go get your fingers entrapped in there. And also, and there are some features that are not useful anymore. Like it had like a middle rod, and it had like a black and white, a grayscale reference, which now we don't need. And also they needed to cast a shadow, to do some calculation stuff, which are not needed. So we got rid of those features to save for weight, and we make it that is safer to use, and also it's about the same weight, but it also its visibility. It has a better visibility since it has bigger stickers than the one previously. For the Apollo mission, that one could get covered in dust really easily, and because stickers were like, I think, a centimeter by a centimeter, they could obstruct the view really easily.
Okay, and how did you determine the stability of 35 degrees?
So what we did a kind of a simulation like your typical physics problem. So we calculate the mass of the rod when it's extended, we calculate the center of mass, we put it at an angle and see until it topples. Our calculation was more like 41 point something, but we rounded down just to be safe. We haven't tested yet, so we want to test it on uneven surfaces to see the actual angle in practice. But it's something that we have to test. But the way that we found it right now was used to calculations.
Okay, thank you, team, and good luck with MicroGenex.
Yeah, thank you.
All right, audience, that concludes our Day 2 showcase event. Thank you to all the faculty advisors for coaching these teams this semester, all the NASA mentors for supporting the teams and giving them lots of good NASA information. All the collaborators, a lot of teams reached out to other experts. Thank you, collaborators and judges. Anybody who is able to give some feedback to the teams, please go to the website, tsgc.utexas.edu/challenge, and download the program. And then you can find the links in there to review the videos that you saw at the beginning of the day, the presentations that were just given now. They'll be on by tomorrow, and as well as the electronic posters that every team created. So thank you, entire audience, online at YouTube Live, as well as here on the Zoom webinar. And students, give yourselves a big pat on the back. You did great this semester. It's really just been 2 months for a 7-month project, so you're not even halfway through, but I think everybody has made really great progress. So that ends our challenge. And if you have more information about Space Grant, check out tsgc.utexas.edu for Texas, or spacegrant.org for our national foundation. Till next time, bye-bye.